Okay, I'm very frustrated right now because all the videos are being messed up, so I decided first off, I should probably erase that, but I decided after that that I'm going to talk you guys through Euler's method because I feel like Euler's method is where this should get a little easier, a little less stress-free, and I can relax. I'm very upset right now. I'm not really that upset. I'm just kind of annoyed, but that's okay. And these videos are taking longer than they should because I had to do the video 3 times. That's okay. So, I'm teaching you guys something today called Euler's method. And what Euler's method is it's kind of a way of approximating when something, okay, basically this is what it's used for. So, we talked about separation of variables, differential equations, and to find what the original equation is. And then the last video with the story problem, we talked about then you can plug in a value and you're basically approximating, or you're not approximating, I'm sorry, you're basically getting another value that's on that line. But what if you get something like this? You get dy dx equals, and we'll do 2x minus y. Guys, there's no way that you can separate variables on this one. Think about it. You can multiply the x over, and then you get dy equals 2x minus y dx. And then you can add the y over here and get y plus dx dy. That doesn't make any sense. There's no way to separate the variables completely. And my papers just fell on the ground. I need those. So, there's no way to separate the variables efficiently to get an equation. Now, sometimes with these you still can, although we're not really going to talk about that. But basically what we want to do is we want to we can actually use something called Euler's method and still be able to approximate values. So remember in the last video we talked about we want to know what time this would equal 0. We're getting a value for the original equation, and this one we're kind of doing, that's what we're trying to find. We're trying to find a value. However, the value is going to be an approximation, and I'm going to show you how this approximation works. So let's say we have a little x and y graph right here, and let's say you know that there's a point like right there. Okay, well, let's say the original line looks like that, but you don't know that, and you want to approximate what the point is going to be right here. Let's say this is A, and this is B, and we want to approximate what's the y value going to be at B. And let's say we don't know this line or equation. Well, what we can do is we can think, well, we're going to be a little off, but let's take tangent lines after tangent lines and try to see how accurate we can get. So think of it like this. If you took the tangent line right here, it looks something like that. And let's say we're going, and what happens in each of these problems, I'll give you a step size. So let's say the step size is going to be, we'll do like this many of them. Well, then we're going to say right here, there's going to be a point. And then if you did the new tangent line right there, it's kind of hard to visualize in here because there's no line, I understand, but if you did a new tangent line, it'd be like right here, and so you get like right there. And if you did a new tangent line, it'd be like right there. And then you get something that's like right here. So obviously, this is a little off because this is the real one and this is what you got. That's also because the line I drew is very steep, but it's a pretty close approximation most of the time, and we can kind of use this mentality. If that didn't make any sense to you, basically I was doing tangent lines that are parallel to these tangent lines, but we don't know what this line is, so we're kind of going a step at a time. And we're going to have to use that knowledge in this case. And Euler's method, you're going to use a chart. So what we're going to do is we're going to make a chart of x and y values. We're going to make a chart with x, y, and then dy, and I'll explain why in a second. So the problem here states that the 2, 1 exists on this graph. And you want to know approximate what y is going to be when x equals 8. The problem also says you're going to use Euler's method with a change of x equaling 2. So that means every step you're going to do, x is going to go up by 2. So we 2, 4, and 6. Okay, so we know that dy dx equals 2x minus y. If you guys remember back to, I believe it was the first or second unit, when we talked about the difference between change in y and dy. Dy would be the difference in the tangent line, where the change in y would be the difference actually. We're trying to look for dy because we're doing tangent lines, because we're making approximation. We don't know what the actual line is, so we can't find change in y. So we want to find out what this is, and then we want to add it to that, because this is what the original one is. The dy is going to be what you're adding to it, because that's the new difference in y. And then you're going to get what the next point is. So for example, if this was 2 and this was 4 or whatever, then you're going to take what 2, which is 1 for y, add the dy, and then you'd get 1 plus dy. So the point is, we need to find what the dy is and then add it to this y. Well, we know that dy equals all of this times dx. So it's going to equal 2x minus y times dx. Now remember that dx and change in x are the same thing, so I'm just going to write delta x. And with this knowledge, now we can plug things in. The dy for this one is 2x, so it's 2 times 2, which is 4, minus y, which is 1, and that equals 3, and then you're going to multiply that by the change in x, which is 2, because remember that's what we're doing, and you're going to get 6. But the last thing we want to do is we want to add it to the original y, because we're looking for dy, which is the difference. We want to know what the y value is, so you have to add to the original one. So this would be 7. 1 plus 6. Do that again. 2 times x is 8 minus y, which is 7. So you get 1 times change in x, which is 2. Add 2 to 7, you get 9. Last but not least, we're going to do 2x, which is 12, minus 9, which is going to be 3, times change in x, which is going to be 6, and add 6 to this, and you get 15. And therefore, you can say that by Euler's method, when x equals 8, y approximately, that's the worst approximately symbol ever, equals 15. That's Euler's method. I think that's really all I have to say about that. It's a pretty simple concept, so